How to calculate distance using reference points. You're watching the video for part 1 of the work plan. The learning target is I can identify and use reference points to calculate distance. This is for step 1. Watch the reference point video on hf6.weebly.com to find out how to calculate distance the air trolley traveled. You're going to complete your notes on page 2 in your new science notebook. Any notes that you need to record will be in blue throughout these slides. Remember, page 2. Everything has to be someplace. In physics, we refer to the place where something is as its position. You have a position, your notebook has a position, and your air trolley has a position. The symbol used in physics to indicate the position is a lowercase letter x. Where have you seen x used to indicate the position of something? That's right. You may have seen it on a pirate map to mark where the treasure is hidden, or on the mall directory to mark where you are currently in the mall. In your notebook, you need to record the definition for position. Position is represented by the symbol x, and it is the location of an object at a given time. Here is the flight line with an air trolley in starting position. I can mark the position with an X. Now, what can I do to show that the air trolley is moved? That's right, I can mark it with another X. But then I have two X's. If X indicates the position of something, it looks to me as though the air trolley is in two places at once. And is that possible? No way! In physics, an object's starting position is called its initial position. Its ending position is called its final position. The convention for showing initial position is an X with the subscript I, written like this. X, I. And the subscript, as you guys can see, is smaller or below the X. In a similar way, the final position is indicated by an X with the subscript X. Once again, we have the big X and the F is smaller. So we have initial position and final position where it ends. Our picture now indicates that the trolley moved, and it indicates the direction it moved. What other information would help a stranger understand the movement of the trolley even better? The distance an object travels is another important piece of information about movement. Distance can be measured in standard metric units like meters, centimeters, kilometers, and so on. Distance is how far a moving object went. The number line is calibrated in centimeters. Let's measure the distance traveled by the trolley on the board. First, we need to determine where to measure from and where to measure to. To do this, we must 1. Draw arrows to indicate where we will measure from and where we will measure to. You guys can see that this has already been done in red on the examples below. 2. We must measure the distance, and 3. We must record the distance. Here, we have, for example A, we have our air trolley traveling from 0 to 85. So our air trolley has traveled a total distance of 85 centimeters. And B, it goes from 10 to 85, so we go a total of 75 centimeters. And for C, we go from 0 to 75, and once again, it's 75 centimeters. So this creates a problem. In this exact instance where our air trolley has gone the same distance, we have 3 different measurements. Well, in all reality, we have 2 different measurements. So what's the most accurate way to do this? It's important to establish a reference point on the object to monitor how far that object moved. We typically use the front of an object as a reference point so we don't have issues with getting inconsistent measurements. If you can see, on this air trolley, we've used the front and the front. So if we consistently measure to that point, we'll always get an accurate representation of how far it's traveled or the distance it's traveled. This needs to go in your notebooks. The definition for reference point is a point on an object that helps you measure how far an object has moved. The Greek letter delta is written as a triangle. Delta is a symbol used in physics. Delta means change. We know that movement is change in position. Delta is change, x is position. Change of position is represented by delta x, or triangle x. Distance is how far something moved, or the amount of change of position. Distance is represented by a lowercase d. This needs to go in your notes. Delta x means change of position. A lowercase d represents distance. Distance is how far something travels, or the amount of change of position. All three of these things must go on page 2 of your notebook. We will use distance a lot in this course. Sometimes we will measure distance, and sometimes we will calculate distance. When we calculate distance, we will use an equation. An equation is what we use in math to plug in numbers, so we always use the same math problem. Work in your group to figure out the equation for calculating distance using the symbols we've learned so far. So the equation that we will use is distance equals final position minus initial position. And your final position should always be greater than your initial position. Now you need to turn to page 3, flight distances. We're going to do the first example together. The instructions say, how far did each air trolley fly? Calculate the distance of each flight using the distance equation. Mark your reference points with arrows and show your math. So, step 1, it says mark your reference points. And we said earlier in this slide that we were going to mark our reference points with arrows at the beginning of the object. So, here's our initial position, here's our final position, and we're measuring each time from the front of the air trolley. Then we need to find our initial position and our final position. Our initial position I'm going to mark in blue, and our symbol for that is X with the subscript I. And here we have 10 centimeters. Our final position I'm going to mark in green. So our final position, XF is the symbol, is 85 centimeters. And then we're going to plug our equation into this formula. So D equals XF is 85 centimeters, and XI is 10 centimeters. So 85 minus 10 is 75, and we always keep our units, which was in centimeters. So we have solved our distance equation.